Hi guys, thanks for coming. I'm gonna try to give as short a talk as I can and then walk you guys in MATLAB through the code that I've provided. So I see you all have your computers and you all have MATLAB, but I haven't seen many people actually with MATLAB open. So while I'm giving a talk, I suggest you go to my GitHub here and you can click download the zip file right here, and you'll download all the files that you need to walk through all the steps of this analysis. And also in that folder, I'll show you is an HTML file that we can walk through the code more easily. Also in the file is the PowerPoint that I'm going to present that you've just downloaded. And this is just maybe 10 slides. To all you guys that just walked in, I just said that you should go to the GitHub here and download the zip file with this green button, because after I give my brief 5 or 10 minute talk, I'm going to walk you through the code together, and I want you to have it open in MATLAB. And also in that code, you'll get this PowerPoint that I'm going to briefly present here. I gave a whole class sitting down because I had an injured leg, and in my evaluations, they're like, it was okay, but I shouldn't have been sitting down the whole time. And I told them it was because I was hurt, but they didn't. They're like, I know he's hurt, but it just wasn't good enough. Oh, and I'm not on the microphone if I go there, so I'll try to stay here. So, as we've seen today, and as you likely know, that we have a bunch of neurons in our brains, and they fire up at the top there, and they tend to fire in relation to the local field potential. And this is always something I thought was kind of circular until you think about the fact that the local field potential is predominantly driven by the depolarization and hyperpolarization of the IPSPs and EPSPs, which is a separate event than the spikes. Still, it seems a little circular, but that's because of the physics of as you become depolarized, you become more likely to fire. And so you have these big groups of neurons that fire together, and this leads to these, and is also a result of these oscillations in the field potentials of the brain, which we're going to talk about today. So if you have a group of neurons big enough, they can create an electric field that's big enough that can even travel through the human or the animal skull, and you can measure it with electrodes on the skull or the scalp more often in my lab. And so you can stick your electrodes on their head and measure the EEG. But all the analysis we're going to talk about today could just as easily apply to local field potential, could apply to Majid's voltage-sensitive dye data, could apply to the stock market data you can download, or anything you want to have a value over time. So you've all seen likely that you can measure ERPs. You can average together time-locked EEG signals and create ERPs, and we're not going to talk about that today. We're going to talk about the frequency domain analysis of EEG data. And when you look at the raw EEG and what Hans Berger and his colleagues in the 40s and the 50s found in Montreal was that the EEG is composed of these different frequencies of signals, and they're bigger in different parts of the head and in different situations. And it's likely the case that these different frequencies represent different functioning of the brain, different states the brain can be in, different states a network can be in. So we want to understand and isolate and quantify these different states by measuring these oscillations. And we're going to focus today on alpha oscillations because A, they're really big, they're easy to see. For many years they were treated as noise and data you would throw out if you were doing ERP analysis if you had too big of alpha waves. They were also the first thing discovered in the 1920s by Hans Berger and his clandestine lab in Vienna, where he was trying to measure EEG because he believed in telepathy, and he thought that EEG might be some way that people were communicating through electric fields across big distances. So these days, instead of looking at raw traces on paper and comparing them to a rhythmic sine wave, we can decompose our data using math. The math has been around for years, but the computational power hasn't. But now we have the computational power on our cell phones and laptops to do these kind of analyses on our massive data sets. So we can take a time series data, voltage over time, and we can decompose it into the sum of sine waves where each one has a coefficient, a beta coefficient or a weight, which can represent the power, how big those oscillations were. So you can think about this like a regression, that you're quantifying these betas, which is how much this sine wave predicts your signal. We're going to talk today about using Fourier transform and also a related analysis, a wavelet analysis, to look at our time frequency data. So now looking at frequency over time. We'll go through code that can do that as well. And so the basic, what we do in my lab, normally we have these chunks of data every time someone heard a sound or saw a picture, whatever it was they were doing. And we take them, instead of averaging them together, we do a Fourier transform and compute the spectra for each one. And then we can estimate things like how much alpha power there was, or how much, what phase the cycle of alpha was in, what part of the wave alpha was in. And I'll talk more about that as well. And I learned this type of analysis to start analyzing some data sets that were these kind of experiments where you show someone a flash of light over and over and over again so many times they want to leave the experiment, and you compare their oscillations when they do and they don't see the flash of light. And you find that they have more alpha power when they miss the flash of light. And it's the same case if you compare times where you do and don't see a artificial flash of light when you TMS someone's visual cortex. The times where you see it, you're more likely to have lower alpha power. So this led us, when I was just starting grad school at the University of Illinois, to do these studies comparing these masked visual targets that are difficult to see. And we wanted to look in this period prior to their onset and look at the brain state. So it's super boring and very difficult to see this target that's presented for 11 milliseconds. Subject responds if they did or didn't see it. And at first we were looking at the evoked activity for the targets that were seen and weren't seen. We were doing a study on consciousness, and we wanted to see what happens in the brain when we're aware of something versus when we're unaware of something. And it's kind of boring. Your brain responds more when you're aware of something. It's interesting, maybe it responds in the same pattern, the same ERP components when you're unaware, but it turned out to be less exciting than what we found when we looked at this baseline period at the onset of the target. So we were getting this paper ready, and I had a number of people tell me, like, what's with this baseline here? It's a little funny, and it looks a little wobbly. And so if you zoom in there, which after ignoring them for like 6 months, I finally did zoom in there, we saw that there's a 180-degree difference in the phase of the oscillations. This is just in the average over all the people and all the trials. And you see that there's a different phase when targets come in and they're missed than when they're detected. So if you think way back to the first slide where I showed you these spikes that happen at certain parts of an oscillation, maybe this makes sense, that if a target comes on during a certain part of the wave, all these action potentials can happen, and if it comes in on the opposite side of the wave, then they can't happen, and you are less likely to say that you see this target. In this study, we also replicated this kind of classic finding that the more alpha you have, the bigger your waves are, the worse you are at seeing things. But then the main finding of this paper is that your brain has a different phase of alpha when you're going to miss a target than when you're going to see a target. And I'm going to show you today some types of analysis that we could do and do together to start to answer some of these questions on some fake data. So thank you for listening to that boring part of me talking, but now it's up to you to do some of the work. So If you want to hear me talk more, I'm giving a talk tomorrow at a symposium. I guess it's like the CapNet symposium. And I'm talking about my student Joanna's research on riding bicycles outside with EEG on in like a series of 5 experiments that she's been doing. But we're going to talk about boring analysis stuff today. So inside this folder that you should have downloaded by now, which I'll just bring up, inside this folder you have an HTML folder, you have the PowerPoint I just gave, you have this M file, which is the main file which we're going to walk through, and you have some functions in these 2 folders. I'm just getting used to GitHub, and I had to copy the HTML into the README of this GitHub. If anyone knows a good way to do that that doesn't look like this and instead looks more like this beautiful HTML code, please email me. In MATLAB, now I'm going to go and open up that file in the folder if my MATLAB doesn't crash here. So in the meantime, I guess you could locate this HTML file, which is in this folder in HTML. There's actually 2 of them that are pretty much the same. One was from last year in Montreal. One was from a recent workshop in Victoria. I think the only thing different is that they say the name of the city in the file. But if you open up that, it's this, this file that'll open in your browser that we're going to walk through as we wait for MATLAB to decide what it wants to do. Luckily, I have 2 versions of MATLAB installed, so I can just do that. So in this file, I make some fake data, and then we walk through some steps like filtering it, and then doing a Fourier transform, doing a wavelet analysis, doing a moving Fourier transform. You can see them all right there. And, oh, and a Hilbert transform, that's fun too. We also epoch the data and make little fake ERPs. And then once we do all these different types of frequency analysis, I show you how you can get the power and the phase values out of those analyses to do some extra fun stuff for your papers. Let's see. So I'm going to go to this folder I just downloaded. And open up this M file so we can work through it together. Okay. So now that I'm in this file, I can do things like run individual parts of it. But I wanted to show you, if you didn't know, that you can, if you want to make an HTML file like this, let me move this out of the way. If you want to publish your code as an HTML file, if you didn't know how to do this, you can go to this Publish tab and click Publish, and it will kind of make a big website that you can put online. But I still would like to have that spit out a README file for GitHub, because that's more useful these days. So that's what I'm going to walk you through here, which is the output HTML file. So you should have your MATLAB over here, and then I'm going to walk you through the code over here as we run the different steps. So the first step here, just add some functions from some of those folders. So the second step is about making some raw fake data. And it talks about sampling rates and Nyquist frequencies. So a Nyquist frequency is half of your sampling rate, and we can represent frequencies in our data in a frequency analysis up to that Nyquist frequency. So here we are, we're going to run this code that's going to create a bunch of fake data. So it's just going to use this random numbers multiplied by 100 and subtract 50. So it's really just completely random. It's not that good of fake EEG data because EEG data has a little bit different qualities, but it'll work for what we need. You can zoom in on a particular set of time here, and you can see that it looks like a bunch of weird data. EEG data would be a little more smooth once you zoom in this period of time. Okay, so that's the first step here. So the next step here is about filtering the data, and this isn't like a be-all, end-all how to filter your data. In fact, I think that would be like a whole workshop we could have on filtering your data in different ways. So this just uses one type of simple Butterworth filter, and you can use this command Illini filter, which we made in grad school, to use it either as a band pass or a high pass or a low pass filter. Right now I'm using it as a band pass filter, and I'm filtering out everything but the alpha waves. So I'm using a high pass filter of 6 Hertz and a low pass filter of 14 Hertz. And I'm calling this Illini filter with that data I just made, with the sampling rate I have, the high pass and the low pass. Order means what type of polynomial to use for your filter, and you can increase that to increase the function of your filter. So we can run this code, and we can see that it takes our original data and it filters it so that it looks just like alpha waves, even though we know that it's still kind of fake data. So we can run that section of our code. On my Mac, I run a section of code. I use this evaluate current section. So it's like command enter. I forget what it is on Windows, but it's a nice little function. And you can create sections of your code with these double percent signs. Create these little sections that you can run one at a time. And you can see that in the HTML, it also treats them as like as a chapter. So we can zoom in on this filter data too, and you can see it's starting to look like alpha waves. You can see how easy it is to make fake alpha waves. You just put some random numbers and filter it into the alpha frequency. So now if we were to zoom out into, say, a second of data between 51 and 52, we should see about 10 cycles in that second. And we can also make it a tighter filter, of course. We could use sharper cutoffs, like 8 to 12 hertz, and then our data will just look even more rhythmic. Okay, so we got this fake-looking data. Looks like alpha waves now that we filtered it. I'm going to go back to 6 to 14 hertz just so that we have a little bit more broadband noise in our data. Okay, so now we're going to treat this like we do with a lot of human data, and I know Arter does too with his data, with a trial structure. So with the humans, we bring them in like you and your friends and stick them in front of the computer, and we present them a trial over and over again 1,000 times. So we know the exact moment that the stimulus came on, and we're going to use that time as the averaging to average a bunch of stimuli together. And we're going to use 100 fake events in this raw data. And we're going to take... yeah, please.
I've got a question. So I don't know if other people have this here, but I don't... my MATLAB says I don't have the filter.
Okay, I think that's because you didn't run this very first box.
I did.
Oh, you did?
Workshop.
And did that work? So then you have to go to the folder where you are. What do you call that? So go to the folder where you've downloaded it. Make sure your current folder is the folder where the code is, and then I think that'll work. Yes, that happened to me this morning too. So once you find your folder and you go into it, which, oh no, now I can't find it. There it is. That should work. But I'll wait because that's an important function. The Illini were a First Nations tribe in Illinois. Yeah. Oh, sure. I'm not, even though my name has the word math in it, I'm not that good at math. But order means that it's like the order of a polynomial. So x squared plus x plus 1 is a second order polynomial. And so then something about filtering is that you create a polynomial filter. Does anyone know lots about filtering and wants to talk about that? No, right? But yes, but basically it's the complexity of the filter, and the higher order filter you use means that do we have any dry erase markers? Not really. So when you filter something, you want to filter just the frequencies that you want to filter and not the other ones. And there's something called a roll-off, which is how much of the other frequencies you're letting into your data. And the ideal filter would have an instantaneous roll-off. It would just filter what you want and not the other things. And the higher order you make the polynomial, oh, wow. So here's our data, and we want to filter out just the alpha. So we want to end up with data that looks just like this after, that's just between 8 and 12 hertz. But inevitably, there's going to be some in these frequencies. And the order of your filter affects the steepness of that drop. And the higher the order, the sharper it gets like this, but you at the cost of something. I don't know. There's always a cost. Thanks to Heisenberg. Did that work for you yet, Tim? Or is anyone else having that problem? Or Claire? Oh, I don't know. 4 would work too here. Let's try. You can also visualize the filter, so you can get MATLAB to visualize that roll-off, and that might help. Yeah. Yes. Yes. Yeah. Right. So you gain in frequency, but in the time domain, everything that happens lasts for longer all of a sudden. Right. Right. You can also open up the Illini filter code and see what it does. It's quite simple. It just makes a Butterworth filter here and uses this filt command with the filter coefficients. So you could also look at those filter coefficients if you're interested in filtering. I usually just use filters that are like built into the toolbox's EEG lab, and I don't even normally use this filter, but when I'm just playing around with the data, I do.
That's working for me.
Okay. Anyone else stuck on the Illini filter? Okay, good. So last step we had was we filtered the data, and now it looked like alpha waves, right? And we were going to epoch the data. So we were going to take this continuous data, and we just pretending we have one channel in our EEG system, and we're going to say that a stimulus happened at all these times randomly in the data. And then we're going to take data before and after the stimulus and treat those as little chunks or epochs of data. And we're specifically going to go from 2 seconds before to 3 seconds after. And that's so that we have enough time on either side of our stimulus to estimate oscillations. The biggest problem I have in helping people do EEG analysis is that they don't ask me until they've already run the experiment. And they run the experiment, and every 200 milliseconds they present a sound, and then they want to know what the alpha waves are like in between sounds or something like that. There's not even enough time to have 3 cycles of alpha between your stimuli. All you're going to see in the data are big evoked artifacts from all the sounds. And so one of the most important steps is designing your task, just like you would for fMRI, where you'd have to really space things out and have slow jitter between them. We have a similar problem with oscillations, because an oscillation is something that unfolds over time. It's not instantaneous in time, so you need to estimate it in some time window. And that needs to be big enough prior, during, or after your stimulus. For the time domain analysis, we use a baseline. So we take I tried to just move the mouse down to the whiteboard. Wouldn't that be cool? We're going to take the voltage in this period before the onset and subtract it, just so all our trials have the same baseline voltage. So this code just picks, where are we here? Picks some random integer times along the data, grabs the chunk of data from before and after, and saves them all in a big list. And so here it is, going through each one, grabbing it from the filtered data. And then I do something else. I add in a little fake ERP into the signal. And I do that with this Hanning command. So just a little kind of a normal distribution. Subtract the baseline, and then it's over. So this is what an ERP analysis would look like, minus putting in a fake ERP. You wouldn't do that in a real analysis. But you would just take your full data, grab all the chunks of data, and subtract the baseline. And then you would normally remove artifacts and some other magic stuff. But finally, you would usually plot the mean over trials. So we can look at that. The top plot is 3 trials, where I've added in that fake ERP. I added a positive thing and then a negative thing. And the more trials I average together, the more the data will come to look like the fake data that I'm making. Will average over all that noise. So you can see that by running this command. If I make like 10,000 epochs, it'll take some extra amount of time, I'm sure. But the noise in the signal will decrease as a function of the number of trials. And if I do 10, then I get more noisy data. And of course, I've already filtered these into the alpha range. So if I hadn't, if this was kind of more broadband data that I just filtered between 2 and 30 hertz, say, then I run that epochs again, then you can see that my ERP looks even noisier. It has that extra different frequencies of noise. But nonetheless, as I get more and more trials, it's going to decrease the noise. So the more trials, the better. The noise decreases as a function of the square root of the number of trials, so there's diminishing returns. If you're planning your experiment, it's hard to pinpoint the number because an extra trial is always better. Okay. So now we've done all these time domain things. So we have our ERP. You could have 2 conditions. You could measure the ERP in both conditions and publish your paper in Science. I haven't seen an ERP paper in Science for a while. So the next thing we're going to do is go through 3 types of frequency analysis and talk about the benefit and the shortcoming of each one. And before we start, I want you to remember and realize that all 3 of these techniques, the Hilbert, the FFT, and the wavelet, have been shown mathematically to be equivalent. If you set the parameters in the right way, they're all doing the same thing, but they're doing it in very different ways. And the parameters are usually set so that they're not equivalent, and you'll see why. So the Hilbert transform, we can take a time series data and we filter it into a narrow band, which is what we already did in our code. We filtered our code just to be alpha waves, and then we can represent that ongoing activity as instantaneous power and instantaneous phase over time. And so I'll show you how we do that. First, I have to go back and refilter this data so that it's, say, between 7 and 14 hertz. So it's just an alpha band. And then we're going to rerun this epoching. Let's make it with 100 trials. Oh, I'm almost out of time. Hey? And then we're going to run this Hilbert transform. And so this is actually just a single trial. So you can see here's the single trial with the added in fake ERP. Here you can see that what the Hilbert does, you can look at the code. It just takes the data that's in epochs here and run this Hilbert. And then you take the real and the imaginary part of that result. So you take the absolute value squared to get the power, and you take the angle to get the phase. And so what you end up with here is the power and then the phase. And the phase I'm just showing in degrees and in radians and in degrees. It's the same data. And what you can see here is the power over time. What you can see is when you put this fake ERP there, you get an artifact that looks like alpha power. And you also get a weird change in the phase, which kind of looks like a resetting of the phase. But you could say that these are kind of artifacts because you know we put this artifact in there. It's not an oscillation. It's not an alpha wave. It's just a normal distribution and then an upside down normal distribution. But it looks like alpha waves here, and that's something to be really weary about, that just because it shows up in a power analysis doesn't mean necessarily that it is an oscillation. And there's lots of researchers that are thinking about this now, of how we define what an oscillation is, how long in cycles should it be, how big the cycle should be. Okay, so that's Hilbert, that's one way. Fourier transform is the second way we're going to talk about. The Fourier transform, we convert our time domain data into frequency domain. And we're going to use this Kyle FFT function, which takes as inputs the data and the sampling rate and an upper bound on the frequencies we want as outputs. So where's that in this code? And the only other thing that I do here is I multiply my data by a window. So I'll show you what that looks like right here. I take the data for that epoch and I convolve it with this window that starts at 0 and ends at 0, so that it makes my data look like this, that it kind of starts flat and then goes up into the data and then ends flat. And this is going to remove artifacts because of the edge of my signal having this sharp drop-off. And then finally we run the rest of this function and we get out the spectra for each trial. So now we have a bunch of these epochs. We have 100 of them. And for each of them, here I'm plotting 3, we have the frequency, the power at each frequency, and then the average over all the epochs. So to test this, we can go back to our filter, and we can start by making a very, very broad filter, and then epoching our data, and then running this FFT. And now you see that it lets in all these frequencies between 0 and 30. And then the more narrow we make that filter, if I now make the filter between 9 and 11 hertz, this is maybe another way to visualize the properties of your filters, because you can see what you get. So this one seems to have some strange properties. It did filter out just that stuff we wanted, but it has this extra stuff it's letting in the lower end. So we might play around with the order to remove some of that extra noise. You can see how much variability there is from trial to trial as well, but on average we're getting this alpha power, okay? So that's, you take a single chunk of data and you convert it to the frequency domain, so you now know that there is this much power in these different frequencies. You're ignoring time. So you might, in that case, that might have been like when someone was meditating versus when they were doing math. You have this big chunk of data and you compare this time versus that time. We want more of a time-resolved measure, what happens during our trial. And so we're going to do what's called a moving window FFT. We're going to do that FFT, but we're going to move it across our data in chunks, and we're going to plot the spectra for each of those movements. So for this moving window FFT, there's a couple more settings. One is the window length. How many sampling points of data do you want to use in your window? One is the FFT length, which is how many points you want of data to use. And this is an important thing that we haven't talked about yet, that if you read the FFT Kyle information, or you read this box, you'll see that our resolution in frequency is dependent on the number of time points we use. And so the more time points that go into our data, the more frequency bins we're going to get. So if you want to estimate really precisely what frequency of alpha someone has, you want to collect data for like 20 minutes and use all that data. Whereas if you just use a tiny chunk of data that's only 300 milliseconds, you can only estimate so many frequencies in that data. And so one thing that we use to cheat is we pad our data with zeros on the sides, and that makes the algorithm act as if there's more data points, and it gives us artificial resolution and frequency. So it looks like you have more frequency bins, and that might help for your analysis, but you're not adding any extra signal into it. So this is specifying the length of the FFT to use. Whereas this previous code here will just use the next closest one it can. The other part about this is that a fast Fourier transform is called fast because it was a trick some mathematician came up with before we had calculators, and they had to do this all by hand, and they found that they could do, I think it's like a quarter as many computations with this new algorithm if the data is a power of 2 in length, 2 to the power of something. So the FFT algorithm automatically adds zeros to your code until its length is a power of 2. Is another part of FFT world that you might now know about and didn't want to know about. Okay, so we specify our window length, our FFT size, how much of that window we're going to use in the data, and then how much we're going to step through our data. We make some output variables to save our data, the power, the phase, and also which frequencies are output. And we're just going to do this for 2 of our epochs. We're going to go through each window, one window at a time, take out the chunk of data, multiply it by a Hamming window, pad it with zeros, and compute the FFT and save it in a big variable together. And then we're going to plot the result. And so what we get are these nice, pretty color maps that you've seen, where you have time on this axis, and at every time you have a spectra that's represented by color. So here you can see that there's alpha power between 10 and 15 hertz. Otherwise, there's not much power. And then there's this little artifact at the onset of our fake stimulus. So that's a moving window FFT. The last method we're going to talk about is a wavelet analysis. So a wavelet analysis, you maybe remember from this code here. This is a good example. Oh, man. So the wavelet analysis, this kind of shows the difference, that an FFT convolves your data with a sine wave that is the length of the data you're convolving it with. Whereas a wavelet uses a certain number of cycles that you can change. In this case, it looks like 5, 1, 2, 3, 4, 5, or 6 cycles. And so for different frequencies, you can see that you're always considering just 6 cycles. You got 6 cycles of this really fast frequency, 6 cycles of this really slow frequency. And this helps if you care about differences in frequencies across different frequency bands. Because if you want to measure a slow rhythm while people are sleeping, and you do an FFT this wide, that means that they need to have like 3 or 4 cycles of the slow wave, and then you'll say, yeah, they got a slow wave, it looks big. But if you use that same FFT and you want to know if they have this fast gamma power, then you need like 100 oscillations. You're not really being fair to the gamma power because you only needed 3 slow waves and you need 100 gamma waves. So that's why this wavelet was developed, that you can get the same resolution in number of cycles at different frequencies. And if you've used EEG Lab before, EEG Lab by default uses a hybrid where you pick the number of cycles, but it increases as a function of frequency. So it's kind of between these two. So it'll start out with 5 and then 6, 7, 8, 9, 10. So you use kind of longer and longer chunks as a function of frequency. You should use wavelet analysis if you want to compare 2 different frequencies in your data, because then you're putting them on equal playing field. If you just care about alpha waves, you can just get away with doing an FFT, and it's way faster computationally. But the code that I have here does a wavelet analysis too. So wavelet analysis is nice because you can pick specifically what frequencies you want. They don't come out of the math of an FFT. So you can pick logarithmically spaced frequencies or linear spaced frequencies. You just specify the number of cycles, 3 cycles or 4 cycles or 5 cycles, and it goes through your data and it does this analysis in this BOSC-TF function, which is a colleague of mine, Jeremy Kaplan at U of A. Where did my MATLAB go? Here. What? Now both my MATLABs are dead. Good thing I'm out of time. Okay. So BOSC time frequency is the wavelet analysis. It takes your data, takes the wavelet, convolves them together, and takes the product and calls that power. It also computes the phase as well. So you just give it the data, the frequencies you want, your sampling rate, and the width of the wavelet. And you get out similar to what you get with the FFT. I'm actually plotting both of the analysis here. Here's the FFT analysis, and here's the wavelet analysis, and you can see how similar they are. And you can play around with different types of data with this code, and you can see when you might want to use one or when they start to give you different results and when they give you similar results. This next part of the code does something similar. You can create artificial data with certain frequencies. So you can have a 6 hertz data or a 2 hertz data. And then it does, so here I'm creating this fake data here, and it does a wavelet analysis to show you the, like pulling out from your fake data, can you pull out that frequency? Shows you the spectra in different ways. The final thing I'll show you before you pull me off the stage, as my MATLABs all explode here, I don't know what happened there, is that how do you do some of these analysis? What's next? What do you do with the data? So what I want to show you is how you can take the power and the phase on individual trials and treat them as the dependent measure. So it's pretty simple, as you would imagine. You kind of pick, oh, I want to know how big the power was between 6 and 14 hertz in the second before the stimulus came on. So you pick your frequency window and your time window. You just go through each of the wavelet analysis and you take the data out and you take the mean over time and frequency, and then you can just plot for this condition, whatever your condition is. This is the power values over this subject's trials. And now I hope you've all taken enough stats to know what to do next to see if that's different in between your different conditions. You can certainly see it's not necessarily normally distributed. Phase is a whole other story, because phase by its very nature happens around a circle. That's how we're representing it. It's not linear. So a lot of the statistics that we're going to use are different. And they represent, for instance, like when you're going north-northwest versus south-southeast or whatever, north-southeast, they're really similar directions, but along a line, they're about as far apart as you could get. And I hope to show you that on these compass plots too, so that, right, if you're pointing this way or pointing this way, the numbers in degrees are really different, but they're adjacent parts along the circle. For phase analysis, you're lucky because there's a toolbox now that you can get that didn't exist when I was in grad school. So someone went and read all the same books in the dusty math library and put all this stuff in a MATLAB toolbox. So you can estimate means and circular correlations and do circular t-tests and all this stuff. Basically, for the phase analysis, we pick a particular frequency and we pick a particular time. Maybe we want to know at the onset of our target, did the trials differ in the phase between two conditions? So then we go through each trial and we take out the phase, for instance, and the power at that exact moment and that exact frequency. And now we can represent the data using some of these plotting options. We can plot, this was all the phases in that condition over all the trials. And it's random, as we expect, because we've made up this random data. This is all the phases. Oh, sorry, this is a histogram of all the phases. This is the raw phases for all the trials. This is the phase and power shown on the same graph. So for every line, the length of the line is the power and the direction is phase. So you might think of some hypothesis that higher power trials have a particular phase or they reset differently. Right, so you could use the same analysis to look at Arter spike data or at the place cell data. It looks pretty analogous as well. You could have two conditions and you could compare the distribution around the circle between the two conditions, within subject, between subject, in different ways. The final step that we don't have time to go into is looking at relationship between oscillations. You can do that in a number of ways. One of the most common is called intertrial coherence. So if you think about that in this regard, here was just our raw trials. And you can see that because of this fake data, every trial, there's this coherent cycle here where they all peak together. If this was an oscillation and they became coherent, they would all start to fire together. It's like when there's a wave in the stadium at the soccer game. And so we can measure that by looking at across trials, how different is the phase. If every phase is the same, so right, we just take a bunch of trials, and they all have a direction, and they all have a direction. And if everyone's the same, then the variance of those trials is really small. It's close to, or how do we say? Let's call it 1. And when they're completely random, it's 0. So that's the intertrial phase coherence. So when it's 1, it means on every trial the oscillations all lined up perfectly, which might happen, for instance, if you're stimulating with electricity. Then the other fun things to do are you can look at how one frequency modulates the power of another frequency. There's some code and information in here about that, modulation index. Whether you have this low frequency slow wave that every time it's in the trough, there's a bunch of power of gamma oscillations. Then if you want to know how the brain's communicating across areas, maybe in your LFP traces or in your EEG, you can look at some of these codes, some of which are in the toolbox phase and power coherence that you can email me if you have more questions, that basically do a correlation of the power between two areas. If alpha here goes up, does the alpha here go up? And does the alpha here go up? So you can do that between every channel and make a big graph that we could hear about how to analyze the graph next. You can do the same for phase coherence, and then that's a lot like intertrial coherence. When two areas are coherent in their phase, there's a consistent difference between the phase. So you just take the phase at each channel and you subtract them and you plot those, and if there's communication, then there'll be a consistent difference. It might not be 0 because electricity might take some time or the axons take some time. It might be 20 milliseconds of rotation, but you can estimate both the the strength and the time of the communication that way. There's other things like lag stuff like Adrienne talked about that we could go into, but I think that's about it. So please ask any questions. Let me know if you get any more bugs. Thank you for listening. Sorry about my MATLAB. Yeah. Yeah, so we're making some guidelines. In my organization, SPR, Psychophysiological Research, we're going to publish like a document of guidelines because there isn't one right now. But you have to be able to justify why you did it. And I guess that's for any analysis. And so you should think about, that it should be greater than some minimum number. You want it to be higher than probably 3, or else it's probably not an oscillation at all. And then you might want that number to be higher than 3 if you think that the state that they're in is more consistent. Like if when I do studies where it's like people with their eyes closed and their eyes open, and I'm just interested in kind of the general state that they're in, then I use like 12 or 20 because I want to know if they're like in this big long period. But if you look in your data and there's little bursts of gamma or something, then you're going to need to use a smaller one because that long one wouldn't pick up these little bursts. So I'd say look at your data first and kind of try to tailor it to what it looks like the oscillations in your data are like. If they're just a couple cycles long, then you might want to use a shorter one. 6 is the other answer to that question. 6. Right, so if you care about, well, not really, because it scales with frequency. So what does matter about the frequency you're interested in is how long of a baseline to use. Because if you care about super slow rhythms during sleep, even if you have a 1-second baseline, that's only one cycle of the frequency. And I guess you could say the same thing about the wavelet. Yeah, like if you care about these really slow waves, then you might be able to use a slower wavelet. But no, I'd say it matters more how long you think in physiology, how long you think the oscillations go on for. But it has to be longer than a number so that you're actually confident they're oscillations at all. Yeah. Right, exactly. Yeah, and so often I'm constrained in event-related designs to make them short enough because things change a lot during the event-related design. So then you probably want to go closer to 3. Yeah? Great question. You should check. So, like, the more confidence you can get in using these, the more confidence you get in, like, changing it to every parameter and plotting the plot for every parameter. We just had a study where we were kind of upset because we were changing one of the parameters and looking at how the data looked over and over again, and that seemed like cheating. So then the plot we ended up using was just like a summary of that analysis for every parameter. And then you can show, look, this doesn't matter at all what parameter we're using. You always get a higher line here than here. So maybe you can cheat at the beginning and look and find the right one, and then you could show in your figures, look, it doesn't matter. It's kind of robust to the parameter choice. Yeah. Does that answer your question?
Yeah. Is stuff like cross-validation?
Yeah, good question. I guess you could, but with different parameters for analysis, or just to like check?
Yeah,
I see. Yeah, I've never seen it framed that way as like a problem to find the right parameters. Good idea. No, so no, but yes, it should be. Yeah, because I've seen that with like the hemodynamic response function. You kind of find the perfect hemodynamic response function, but not necessarily with like the order of the filter you're going to use. Good idea. Yeah.
So maybe just one point to make. So you talked about EEG.
Yes.
But you could apply all of these same filters to LFPs and then also to imaging data.
Yeah. Yeah. I use optical imaging data, and we use the same thing with our light data coming out with fMRI, just slower oscillations. But yeah, any data you can think of, I think. Yes.